Thank you for having me. I will describe the most recent experiences of the Italian Space Agency with Cubesat missions, and in particular the ones that went beyond Earth orbits and the ones that became interplanetary, which are, by the way, the first satellites made by Italian team that can explore this region of space. So we have several initiatives in ASI. Mainly in the past years, I was also promoting initiatives that started from supporting of university initiatives in cooperation with in an international environment. But then we moved to an approach that is more structured for building also constellation of CubeSat for scientific purpose. And currently the agency is running a very well-structured program for development of technology and scientific CubeSat. The two ones that I will mention, first one is ArgoMoon. It's a 6-year CubeSat that has been selected by NASA, being one of the 13 secondary payloads that were part of the Artemis 1 mission. They were supposed to be released along the track of the ICPS stage when the Orion capsule has been already released towards the moon, and the ICPS stage will release in different moments of the orbit that were called bus stop. And ArgoMoon has been selected to be one of the first, with the aim of orbiting close by in the vicinity of the ICPS stage and capture pictures of the this element of the SLS rocket that was supposed to fly for the first time, also being a very high interest, having information of its status during the first phase of the trajectory. And so ArgoMoon features were having based mainly on COTS components and rather hard, but having very well specific subsystems allowing this phase of vicinity maneuvering and trajectory, and also a very accurate pointing and attitude control. In the second phase, ArgoMoon was supposed to have an autonomous scientific phase with flyby of the moon and capturing pictures of this of the Earth and Moon system. This is the timeline that we had in mind to accomplish this this mission. And in the first phase were very critical. In the first hours, the deployments was supposed to be after a few hours after the liftoff. And after the release, there was an expectation of having this first acquisition through the DSN antennas and controlling satellite from the Mission Control Center that has been established in Italy, in Turin. And after that, the satellite will have some autonomous maneuvering. As I mentioned, the timeline was really tight, and we expect to have in the first 10th of seconds this autonomous phase, and after that the orbital maneuvers that will allow the moon flyby. Again, we negotiated with the DSN the set of communication windows for having a good coverage. As you can imagine, during the Artemis 1 mission, there were lots of other CubeSat and payloads that requested the support. And in fact, there was very intense traffic for DSN people to identify all the elements and then provide support and during the communication windows. We had an allowed distance from the ICPS for safety aspect, and also an allowed cone of visibility, because there was also the possibility to capture images of the engines, and this is why our data were encrypted for this. And in the second phase, they were supposed to have this moon flyby and having interesting imaging of the moon surface. At the end of the design process, this is what we gained. This is the main technical aspect of this 6U platform, equipped with 2 optical payloads with different fields of view in order to have a complementary capability of target identification, I mean ICPS, but also having an imaging with a sufficient spatial accuracy and spatial resolution on the surface. So the communication were supposed to happen in X-band with the Iris radio. And after an intense phase of integration and testing, of course, we had the training of the software. Onboard software was probably the most challenging subsystem and element to be developed, because it must be trained and make use of machine learning in order to be able, working in different layers, to identify the targets in the field of view and to maneuver the satellite and control the attitude in order to keep them in the field of view of the cameras during the whole phases. As I mentioned, we prepared a mission control center in Italy, but we made use of DSN antennas that allow us to have a continuous coverage and communication with our satellite. ArgoMoon integration has been completed in spring 2021, and then we accepted as agency and we shipped to the launch site to be integrated in the Orion stage adapter, together with the other secondary payloads, I mean the other Cubesat. There were 10 over the 13 that were selected. SLS has been launched last November after several attempts, and ArgoMoon has been released for about 4 hours. Due to a not exactly nominal condition at the release, we had an initial phase that moved the satellite to the safe mode for a certain amount of time, because the tumbling was a little bit over the threshold of 10 degrees per second that had been set on board. So in the first tens of seconds and then hours, the satellite was not able, unfortunately, to capture images of the ICPS. But the second phase of the mission has been accomplished as per the plan and the timeline on board. So we had several imaging of the moon and the moon surface and also of the Earth while we were passing by. In 2017, on the occasion of a meeting at the Italian embassy, there was for me the opportunity to present Cubesat as initiatives for international cooperation. At the same meeting, there was the Andy Rifkin, which was the scientist of the DART mission that presented DART. And there we had the first opportunity to talk and to think if a satellite similar to ArgoMoon could accompany a DART and acting as a kind of witness of the DART impact, and in particular the effect of the DART impact in terms of the plume of the material that could be generated, that was supposed to be generated by the DART impact, and also having a privileged point of view, because the DART impact effect, NASA planned to monitor them through telescopes from the Earth, while LICIACube could act as a kind of witness in situ and monitor the evolution of the plume, and also having the opportunity to image the not visible side of the Dimorphos asteroid. So LICIACube became part of the DART and ERA missions as part of the first active planetary defense initiative. The selected target is a double asteroid system whose main element is called Didymos, while the secondary has been named Dimorphos, and it is kind of small moon around the main asteroid. And so what we were expected to do was to be released by DART a few days before the impact, travel with DART as a piggyback, and then be released a few days before the impact, and start maneuvering and navigation in order to perform a flyby of the asteroid and to be able to capture images of the effect again of the impact itself. This was the ConOps and what we expect to perform. The very challenging aspect was due to the fact that, as you can imagine, DART was intentionally very fast against the asteroid. And so it was flying at around 6 kilometers per second against the asteroid. And LICIACube has been released like a few days before, but with the limited capability on board, it was not possible to reduce the velocity, the relative velocity so much. So in the end, our flyby was very fast at about, again, 6 kilometers per second. And the other really challenging aspect was to make an autonomous system on board to maintain the during this fast closest approach, to maintain the best pointing. We involved a scientific Italian community, the one that were active in the small bodies studies. So together we agreed on the scientific objectives that were, of course, focused on the plume, because again, as I mentioned, from the Earth, there was monitoring by the other observatory and telescopes, also in orbit. And then the ERA mission will visit the asteroid in several years. So our added value, very important, was to monitor in situ what is going to happen and to give information of the plume evolution. And again, another privileged point of view was the non-impacted hemisphere that could be visible just after the flyby. Keeping this in mind, we again prepared this industrial and scientific team, and we had also strong coordination with the American side, with the agency and the Planetary Protection Office, but also with the APL people in Baltimore that were in charge of the preparation of the DART mission and the conduction of operations. And also JPL has been strongly involved for navigation and for the ground segment. Another very critical aspect was identify the best trajectory, because the flyby was very fast, and we would try to pass as close as possible for having a good set of details, so having a good spatial resolution on the surface and of the plume. But at the same time, we want to be safe enough and not being impacted by the pieces that we expect to be generated by the impact itself. In fact, being focused on the plume, we decided to pass at about 3 minutes after the impact, so that the plume will be really well generated and we can follow the evolution and identify several structures inside this generated material. The team was very busy in optimizing the trajectories, identified the possible maneuvering to maintain the best point of view during this flyby in a safe way, as I mentioned. And of course, everything was affected by a certain uncertainty, but everything was, included in our software, onboard software, and controlled also from the Earth. We optimized the timeline of the closest approach in order to devote different phases to different targets. And so we had the first phase when we're focused on confirm the DART impact. And then we have the observation of the ejecta that I mentioned, observing the back, what we call the backside. We realized that imaging of the crater on Didymos surface would not be possible due to the fact that if the plume was really well developed, the surface was not visible because of all these materials ejected. This is the design, and I think it's in size, of course, very similar to ArgoMoon. The payloads on board had a different set of features that were optimized for this application. And in particular, one of the cameras was an RGB cameras that will allow to identify different bands during the observation. The development phase was very intense in the last years, and we were able to deliver the satellite in 2021. And it has been launched in November together with DART from Vandenberg. We've flown on a Falcon 9 rocket, and as planned, after 11 months of cruise, DART started with the identification of the two asteroids as a target for the impact. During the cruise, we had intense checkouts, and also we were able to charge batteries of our small satellite, because it was like passively accommodated in the dispenser that you can see in the picture. In this case, the ground segment was a little bit more articulated, and the architecture is the one you can see. It involves the flight control team, of course, and the two navigation teams in parallel in Italy and the US, working independently on the solutions to optimize the maneuvering. And also we had a scientific control center in Italy that received images and can transfer them to the control center in the US, and to be shared with the colleague of the NASA and the PL of the DART scientific team. The Mission Control Center and the rest of the ground segment has been intensively tested, and has been all the connection has been checked in different possible conditions. We worked a lot also on the optimization of the process. The time for this maneuvering was really short, so we tried to optimize the process for the definition of this maneuvering that will allow to pass in this very specific corridor close to the asteroid. We planned the 3 maneuvers and one for calibration in order to be sure that the thrusters were performing as nominally. And also we optimized the communication windows around this maneuver, and of course considering the DSN availability for that, before and after the flyby. And so after these 11 months of cruise, on the September 11th, LICIACube has been separated from DART 15 days before DART's impact, and start operating autonomously, and with the initial acquisition and the update on all the elements on board, and start targeting themselves. And also we had an intense calibration phase for our payload, pointing known sources and stars, and having features, and so tuning our parameters of the imaging for our 2 payloads. And as planned, after 15 days, DART targeted the secondary of the double asteroid system and impacted on the amorphous surface. And it was complete success on NASA side, of course. And after 3 minutes, LICIACube passed as planned. But we didn't know, of course, we didn't have the real-time communication. Our communication window after the flyby was planned like 3 hours after, yeah. And yeah, so the flyby happened in an automatic way, and it was blind for us, but the system captured the planned images, like for more than 400 of them. And in fact, after 3 hours, we had the opportunity to download the first of them, and you can see how it is the result. You know, everyone was super excited because we realized that the effect of the impact was much more intense because of the nature of the asteroid. In the end, it resulted that the asteroid is not very rocky and body, but is a rubble pile type. So the impact generated a plume that was much more evident, and then it grew for hundreds of kilometers. And then we were all excited in the control room. And first of all, you can see that the moment when these are the part of the first images that can show us the approaching phase and the phase when the satellite was flying behind the double asteroid system. The plume is very well developed, and also you can see in the left corner the moment of the dart impact, few seconds after dart impact, before and after. So you can see that yeah, there is an increase of luminosity due to the fact that the albedo of the system, of course, increased. So compared to what we expected, a very small cone of ejecta, we had a very large ejection of material in several directions, which was an important information for our scientists. And also they observed that after the plume was well developed, and in the phase when LICIACube was passing by, there were lots of there was kind of an effect of separation of the plume from the surface. There are investigations about it, and we were able to image the not visible side of Didymos, the main, and also the Morphos. So they were able now to reconstruct the shape. They are creating what is called the shape model of both the asteroid, which is a very interesting information. Using also this information, but also measurement from the Earth, NASA was able to confirm the effectiveness of the deflection technique. As I mentioned, the purpose of the DART mission was to deflect the Dimorphos asteroid, change its period of rotation around the main asteroid, in order to check if, in case, in the future, we'll be able to change the trajectory of a possible dangerous asteroid that can be on a trajectory towards the Earth. So in this case, they were able to measure a change in the duration of the period of about 32 minutes, which was a lot. It means that the approach of impacting on a surface and transfer energy was very effective. And also we had the opportunity to separate the contribution of the DART impact, but also the ejection of material contributed to change the trajectory itself, and so the period. I can say that, yeah, LICIACube had lots of the scientific results were very well recognized, and also, as you can imagine, the outreach effect is really intense on the public, you know, because this kind of application has a strong impact, of course. So there was a large interest in the public and the recognition, and also, you know, meme and funny approach to this mission that had a strong again impact, not only on the asteroid. And we were also able to image the Earth and the Moon from that distance. Everything happened at about 11-12 millions of kilometers from the Earth. So we used this platform that was the first Italian satellite that moved so far from our planet to perform different imaging. As I mentioned, scientific team is strongly involved currently in the analysis of the about 400 images. And so now they are finding additional information on the nature of the asteroid. They are deeply investigating the structure of this ejection of material, and how that can be correlated to several other phenomena. We are very proud that recently there are already 5 papers published on Nature, but several other a large work is in progress. So we expect several important results to be certified and distributed to the scientific community by scientific journals. So, in conclusion, yes, these two missions represent a very, very important first experience for the Italian community to participate in interplanetary challenging missions, and confirming also the potentiality of the small sat to accompany, being part of traditionally sized probes or satellite and support mission with a specific, very specific tasks. In this case, the imaging and also being well supported by orbit determination led from the Earth, but also an autonomous onboard system that was intensively trained for this task. I think this is my last. Thank you for your attention, and don't hesitate to write me if you are interested in information about these two missions. Thank you.
Thank you, Simone. We greatly appreciate your time and providing great insights during this presentation. So we have a couple of minutes, which we have a couple of questions, if it's possible for you to answer still. One is coming from Mikhail, where he's asking how LICIACube took pictures behind the asteroids. Did it turn around during the flyby or had cameras on both sides of the satellite?
No, it was, as I firstly mentioned, the attitude has been controlled during the whole flyby, keeping the asteroids in the field of view. So the satellite was really maneuvering and slewing in order to keep this pointing. And this was the most challenging part, because as you can imagine, that velocity, the necessity, the need of turning was very high, and we were at the limit of the capability of the reaction wheels.
And lastly, we have a question from Olga, where she asks, has LICIACube missions completed all its tasks?
Sure. Yeah, definitely. Yes.
Okay, well, good answer. Thank you for the answer.
Yeah, we achieved all the objectives, scientific objective and technological ones. So we are completely satisfied with it.